So this is the first in a series of video-based lessons that will demonstrate the application of linear programming in a number of business scenarios, ranging from operations and logistics to finance and marketing. In addition to the applications presented in these videos, there will be several in-class optimization application exercises to provide additional practice and hands-on experience with practical optimization modeling on a variety of different problems. This material is covered in Chapter 14 of our textbook. There is a number of relatively standardized or generic linear programming models in the areas of operations, finance, and marketing. By studying these different types of models, we will gain valuable knowledge, practice, and skill that will allow us to tackle more complex, less standard problems. Some of these conceptual examples include product mix, process selection, such as make or buy, and multi-period production planning in the area of operations. The others include transportation and other models in the area of logistics, portfolio selection and investment models in finance, as well as advertising allocation in the area of marketing. We start by discussing the different types of constraints we are likely to encounter in linear optimization models in practice. Generally, formulating the constraints correctly, making sure we don't miss any, and understanding the relationships between them is the most difficult aspect of this process. So, it helps a little bit to understand the 5 different types of linear constraints described in this and the following slide. First, simple bounds are constraints on a single variable, expressed as either requirements, such as at least $10,000 must be invested in stock A, or limitations, such as do not produce more than 100 units of a particular product. And it is these two words, limitation and requirement, that describe the majority of linear programming constraints. Limitations generally refer to allocation of scarce resources, such as raw material and labor. Requirements, on the other hand, specify a minimum level of performance, such as meeting the customer demand and exceeding the required rate of return. Some of the slightly more complex constraints involve proportional relationships found in problems that involve mixing and blending, such as in oil and gas, pharmaceutical, food, and financial industries, just to name a few. Quality of gasoline per gallon sold must exceed a specified threshold, and this implies a ratio of 2 values, or a proportional relationship. The last set of constraints are the so-called balance constraints, where, in general, an inflow of some quantity of interest at a given point in time must equal the outflow, moving towards the next time period. Inventory and cash balancing constraints are the 2 main examples we will demonstrate in this series of videos. Finally, there are constraints, either implied or hidden, that is not explicitly stated in the problem statement, so we need to be careful not to miss them. The first of our 4 application models in this series of videos is on optimizing make versus buy decisions. It is important to highlight, however, the first of a set of Chapter 14 models, the template for which is contained within the reading subfolder of the Zura 4 applications folder. Although I'm not going to go through the 8 Chapter 14 exercises in either videos or classes, just like I did in any the other chapters 11, 12, or 13, they are great examples you should do on your own as part of your chapter readings. So the first of those from the chapter 14 here, is CAM Textile, which is faced with decisions on how many yards of fabric to produce on their own looms versus purchase from the outside supplier in order to meet customer demand at the lowest cost. The constraints involved in this make versus buy model include production time and machine capacities, and the objective function includes the company's own production costs as well as the purchasing costs from the supplier. The mathematical models for each of the 8 Chapter 14 examples are also included in the textbook. And although we are not going to be writing these down for our own example, it certainly helps better understand how the theory and practice work together hand in hand. Finally, the information from the sensitivity report, I'm talking about the CAM Textile example here, includes a number of simple yet informative charts in the textbook, ranging from optimal solution and capacity utilization charts to reduce cost and shadow price summaries with allowable range visualizations. And we'll do some of it, not as much as it is in the chapter, but some of it in our own example coming up next. So our own example of make or buy model is similar to Chem Textiles, but is a little bit simpler and more suitable for video recordings. General Flextronics, our fictitious company, must choose how many of its three electronic components to make in-house versus buy from a supplier in order to satisfy customer demand at the lowest possible cost, and within the wiring and assembly labor constraints. So, you can see from the formulation, it is very similar to Chem Textile, but the number of products is smaller and there's no distinction between different types of machinery, the OB versus regular looms in Chem Textile example, and in certain other different minor differences. Okay, this is again where we switch to the hands-on portion of the videos by opening lect3 underscore make or buy Excel file, this guy right here. Notice that obviously the cost to buy each of the three components from a supplier, right, or outsource it, or however you want to think of it, is higher than the cost to make them in-house on a relative basis, right? If we briefly divide the two, okay, if we briefly divide the two, you will see, after you format it to 2 digits, that the component 1 has the highest relative difference, about 17%, right, with the other two relatively smaller, 13 and 12%, right? So we'll delete these before we proceed. So let us start by simply trying to see if we can produce everything in-house. Of course, we can't, or we won't be able to. But if that were possible, it would clearly be the best way to proceed in terms of minimizing the total cost. So look at the demand, 28, 1900, and 1000, and enter it, or copy paste it, if you will, into the number of units to make in-house for components 1, 2, and 3 in row 16 of the model. Okay, so just for show, we'll enter the 3 zeros here as well for each of the three components to currently buy from the outside supplier, right? So the total, of course, which is one plus the other, matches the demand, because that's how we got those numbers. Now let's go scroll down towards the bottom and calculate the number of wiring and assembly hours required by the current production schedule for each of the components to be made in-house, right? So the wiring of 2800 components, okay, at 1.5 hours per each, right, translates into 4200 hours, and a similar calculation is made for the other two, and assembly for the same 2800 components at 1 hour per unit for component 1, and then similarly for the other two, is calculated below, right? Adding up the total hours for all three components for wiring, and the same for assembly, shows us that 8600 hours is required under the current all in-house, right, production scenario, which is well within the available 9500 hours shown above here, right? But also notice that the 6650 hours, right, needed is way above, significantly above the 4900 hours of assembly available. Okay. Next, what we want to do is identify one of the three components that is contributing the most to the excessive number of assembly hours, right? So on per hour, or per unit I should say, basis, that's clearly component 2. If you look at it in terms of the total, which is of course then dependent on the demand, it's still slightly higher for the component 2. So it should be obvious that the next step is try to outsource a certain amount of component 2 production, all right, or component 2 unit demand to the outside supplier, right? So before we do that, though, let's calculate the total cost for what is currently an infeasible production schedule, right, in this green cell the bottom right corner. Although we are not buying anything yet from the outside suppliers, right? We must include the buying decision cells in row 17 in this calculation, because clearly we'll have to outsource at least some, presumably component 2, to make the whole thing work. So the sum product formula must include both costs to make and buy from rows 5 and 6, comma, okay, and all the decision variables to produce in-house and buy from the suppliers in rows 16 and 17, to come up with a currently infeasible cost of a little over $417,000, right? Keep saving, of course, as we work through this. Now, let's outsource, okay, 900 out of these 1900 component 2 units that are demanded by the market, right? In other words, make 1,000 in-house and 900 purchased from the supplier, right? So when you do that, notice that the cost went up by about 10,000 from 417 to 427, okay, but the number of assembly hours went down significantly from 6,600 to about 5,300, right? A drop of about 13 and 1,400 hours, right? Adding another 100 to number of components to buy and reducing production by the same amount get us another step closer. So 900, 1,000, okay, with about a little over 5,000, right? Getting close to 4,900. The cost goes up, slightly about $1,000. Okay, and finally, if we decide to make, for example, 700 components in house, 1,200 outsource, then the assembly hours, right, are now just under the available number of assembly hours, 4,850 versus 4,900, and the cost went up to about 430,000. Okay, our next stop is, of course, not to continue with this manual process of searching for the optimal solution, but use the premium solver instead. So, in these, in examples in the book, generally, a lot of them start by, just having a zero solution or zero, zero for all the decision variables, and then the answer and sensitivity report, sort of have those, zero solution, right? Or no solution really, and the optimal solution. What I'm going to do is I'm going to, because I'm discussing this manually, right, to sort of make business sense out of the whole thing, I'm going to keep these guys as they are. And a lot of times in these simple examples, they're going to be very close, as you can kind of tell here, to the optimal solution, which is fine. Okay, so we're going to launch the premium. We're going to save, launch, the premium solver under add-ins, premium solver. We're going to click on the objective function and change, I guess. Delete whatever is there. Sometimes these references are hanging on, although I deleted them before. Let's see. Click on E25 in this case, and we need to, of course, minimize it. I'm not sure why is it inserting, the whole path. The variables are the production schedule in-house, as well as number of units to buy in rows 16 and 17, as we discussed a number of times. Then the number of wiring and assembly hours used has to be, of course, right here, has to be, of course, less than the number of hours available. Okay, and finally, the demand, right, has to be met, right, has to be met by the total number of units either produced or outsourced. We're going to add, look at the total number of units, which is the combination of, in-house and outsourcing, has to be at least the demand shown in the data section here. Okay, make sure that unconstrained variables are non-negative, and you have the LP quadratic model, and then run the solver. Okay, make sure to select the answer and sensitivity report. We're not going to do it for every single one of these, models, but this one we will do because we want to use it for analysis, and we also want to demonstrate some of these visualizations that are sort of alluded to, for which the CAM textile was used in the book. Okay, so I'm going to click OK. We'll quickly notice that the solution is, of course, very close to what we had, right? A little bit more of the components made in-house, and a little bit less outsourced to hit that assembly hour constraint exactly, and then the cost is marginally reduced within $1,000, right? I'm going to move that tab to the left and have the answer and sensitivity report to the right, and I'm going to, between the video recordings, clean up the answer report and sensitivity report a little bit, and then I will continue them.